All right, gang, here we go. This is for Chem 2 Unit 10, talking about Le Chatelier's principle. Very, very popular, hugely popular. All right, so Le Chatelier's principle describes what occurs to a system that's at equilibrium if we do something to it. All right, so this is the proper definition. It says if a system that's at equilibrium is disturbed by a change in temperature, pressure, or a component of concentration, the system will shift its equilibrium position so as to counteract the effect of the disturbance. So let's just think about this real quick. And I find it easiest to think about it in terms of reaction rates because you guys are all good now at reactions. I don't know why I put D before C, but it doesn't really matter. So you guys are all good at thinking about your reaction rates, right? And thinking about those things that can increase your reaction rate. And thinking about, well, if I do, if I increase concentration, my reaction will go faster. If I increase temperature, my reaction will go faster, et cetera, et cetera. If I increase pressure, if they're gases, the reaction will go faster, so on and so forth. So the same kind of idea happens here. All right, with Le Chatelier's principle. But remember, an equilibrium is established when the rates of the forward and the reverse reaction are equal to one another. So if we're going to do something to change our reaction rate in one direction, then that means that the rates are no longer equal to one another. And so we call that a shift. Okay, so for example, if I have A and B that are in perfect equilibrium with D and C, that means that A and B are reacting just as fast as D and C are reacting. So there's no net change in amounts on either side. But if I say, well, I'm going to take a big old scoop full of A and put it in my solution, well, what occurs is because now there's more reactants of A and B, the A and B reaction going in the forward reaction will go faster. Right, and that makes sense. If there's more of them, they'll speed up. Right, that's what we talked about when we talked about reaction rates. Okay, and so if A and B speed up in reaction rates, that means D and C didn't speed up. Right, when I first dumped in A, D and C are still going to be going just as fast in the reverse reaction, but A and B are going to speed up. So therefore, A and B are going to speed up until they slow down enough, and D and C speed up enough that they are now at equilibrium. But now my entire equilibrium point has shifted slightly towards the product side. All right, and so you could imagine like, well, I'm going to end up with more D and C than I did before, right? I'm farther to I've shifted more to the right or more to the product side. Okay. And so essentially what we're going to do is talk about, well, why does that occur for all of these different things? All right, so this is a really great graphic that's in the book here that kind of individually shows you those three things and what can occur: your concentration, pressure, and temperature. And we're just going to go through, you can pause it and take a gander at this or come back to it after the video is over. And we're just going to talk about each of these three things individually. All right, so if we change concentration, all right, so this is what would occur if we change concentration. And this one I think is the easiest to kind of picture what's going on. So if the system is at equilibrium, so this is the point we're at initial equilibrium. We've got N2 and H2 in equilibrium with our NH3. And then it says adding a reaction component will result in some of it being used up, and then removing a reaction component will result in some of it being produced. Okay, so let's talk about what that means exactly. So yeah, I just want to make sure there was another slide for concentration. So if we add H2, okay, during this point, all right, we've added H2, so that means at this point, the forward reaction will speed up, right? And then as we progress, before we reach equilibrium again at this dashed line, the amount of H2 will decrease, and it'll go down from what it was to start, but not necessarily as low. It just kind of depends on how much you add, so on and so forth. All right, and so it's going to decrease. Notice that the NH3 increased, all right, and then the N2 had to actually go down because we know that N2 and H2 had to react together. If we only added H2, that means the N2 had to have been lower than what it started with. Okay, so that one's pretty easy to understand. If we added H2, the right reaction would speed up, and so then we'd have to shift to the right. Now imagine what would occur if we removed something. So instead of adding H2, okay, we took away H2, so we added something in there that H2 can react with aside from the N2. All right, H2 is also less dense than N2, so it would be reasonable to assume that we could really just like open up a valve at the very top and H2 would escape and N2 would mostly stay in there. I guess H2 is less dense. Right, I don't know how much more less dense it is, but anyway, and so you could imagine like if we were going to just ignore these lines right now, if we took away some of that H2, right, okay, the H2 would be down here, And then, so that means the reaction in the forward direction would slow down. So that means we'd shift back to the left, right? And so we'd end up, our H2 line would go somewhere like this until we reached equilibrium. Well, what would happen to our NH3? Well, the NH3 was here, but if the reaction shifts to the left, that means we're going to end up with less NH3. So it would come out somewhere like this, and we'd establish equilibrium there. And then what would happen to the N2? Well, the N2 didn't disappear, so it's going to be exactly where it was when we put in that disturbance. And so we're shifting to the left, which means we're going to make more N2, so the N2 will shift up somewhere like this, right? And so those red lines kind of give you an idea of what's going on. Now, the easiest thing that I find is just think about what's going on when you're doing, and you guys know this, I always rely on like logically think through what's happening as opposed to just memorizing it. You could just memorize these bullet points. Adding a reaction component will result some of it being used up, right? If you added NH3, you're going to use some NH3, right? And then the second bullet point, removing a reaction component will result in some of it being produced. If you remove NH3, you're going to make some NH3. All right, but really, like that only gets you so far. I highly suggest thinking through it. Think about it in terms of, if I add this molecule, if I add this atom, or whatever it may be, what happens to my reaction rate? If I increase my reaction rate in that direction, what does that do to everything else that's in my system? All right. Next one here is in volume or pressure. All right, this really only works when you have gases. I mean, that makes sense because your liquids and solids don't really get affected by change in pressure because they're very dense already. There's not a lot of room for them to move around. Their intermolecular forces keep them very tight. Okay, so if you change the pressure or volume, it'll affect your equilibrium. All right, so in the middle here, we've got two A's are in equilibrium with B. All right, and so there's two ways we can increase the pressure. We can decrease the volume, or we can add more of whichever gas we want to. Now, you have to be careful, because if you add gas, then that also increases the concentration, which leads us back to what we just finished talking about. So specifically, so if you're going to increase pressure by adding more, okay, then that means you have to add them at the same ratio that they were at the initial equilibrium. So you're just purely increasing the pressure instead of also increasing the concentration. But whatever. All right, so if we increase the pressure by decreasing the volume, that means their concentrations do go up, but they go up equally. But what actually happens is, if we increase the pressure, then the side that has more molecules that are colliding are going to speed up more, because, like, for example, this A value here, okay, is going to, these guys are going to hit each other more often than they were before, so this reaction is going to be shifting to the right, because this reaction going in the forward reaction is actually going faster at a lower pressure. All right, because these guys are going to, if they're in a smaller space, that means they're going to be hitting each other more often. Their partial pressure is higher. All right, and then B here, this reaction rate will probably remain close to the same, because these guys don't have a collision at all. This is a purely decomposition reaction. All right, so when we decrease volume or increase the pressure, your new equilibrium will always favor the side to reduce the total number of moles of gas. Okay, let me erase that so you can read it a little. Oops, no. All right. Reduce the side, the total number, it'll go to the side that reduces the total moles of gas. Reduce total moles of gas. All right. Now, if you go the opposite way, you increase the volume and thereby decrease the pressure, you're always going to favor the side that increases the total moles of gas. And, like, you can think about it the same way. All right, if you increase the volume, that means the side that has more moles of gas, this A here needs two of these guys to increase each other. If you've increased the volume, that means you've decreased the pressure. It's less likely for these A molecules to hit each other, so it's less likely for them to have a successful reaction. So therefore, it's going to shift to that side. Okay. Now, change in temperatures. Okay. Really, what matters is if it's endothermic or exothermic. And so in an endothermic reaction, your heat acts like a reactant. And that makes sense, right? Think about it this way. You got A plus B. It's an equilibrium with C plus D. And if it's endothermic, that means it's going to take in heat. So you could think about your heat as a reactant. So it looks something like this. Now, and then at that point, you can just establish the fact that it's acting like concentration. Okay, if we added a reactant, it would shift to the right. Or if we took away heat, it would shift to the left, right? And same thing as concentration. And then exothermic reaction would look exactly the same, only the heat would be on the other side. C plus D, and then plus our heat. All right. So here they've showed you here a reaction. It looks like I got cobalt hexahydrate ion. Okay, it's kind of, oh, this is, yeah, okay. And on the left hand side, it's actually an endothermic reaction. So when you go from if you're favoring this side, you're pink, and if you're favoring this side, you're blue. Okay, and so if you heat this guy up, that means you're adding a reactant. Okay, and so it's going to make the reaction going from the forward reaction speed up. So you're going to shift to a blue color. In the middle, it's kind of a purpley color, and then adding heat will make that solution and that mixture shift towards the right, and so therefore you get this nice blue. And then vice versa, if you put it in like an ice bath or something, cool down that temperature, that means your reaction going in the forward reaction would actually slow down because you're removing a reactant. Okay, and so therefore the exothermic side of the reaction, all right, will speed up. Okay, and so you'd shift to the left, and therefore you get that pink color. All right, exothermic equilibrium. Now this is pretty interesting. They threw this in there just for funsies here. But so we talked about the Haber process before a couple of videos ago, and we use it to produce ammonia from elements. Okay, now it's an exothermic reaction, so you'd think, so it would be like, so this would be N2 plus 3H2. It's an equilibrium with 2NH3. That's the Haber process, right? And they say it's an exothermic reaction, so that would mean that our heat here is on the right-hand side. Okay, and so you'd think that if we cooled down that reaction, you'd result in more products. Now the problem is the activation for the energy for this reaction is really, really high. So if you add if you take away heat, then the reaction just doesn't have enough energy in order to continue reacting, and so your reaction just kind of stalls out, and so it doesn't have the forward reaction has such a high activation energy that it's just not going to work. So this is one of the big exceptions where you can actually affect your equilibrium by using a catalyst. Now remember, when we talked about reaction rates, we talked about catalysts. We talked about how a catalyst changes the reaction mechanism. And so we talked about how, let's see, let me get a blank slide here. Okay, and so we had our energy profile, right? And so this was our change in energy, okay, and this is our reaction progress, okay. And we talked about how we could have a reactant going somewhere. This would be an exothermic reaction. So your reactants over here, your products are down here, right? This was your activated complex, okay. And so this guy here, this was your activation energy. Okay, that difference between those two. And then we talked about, well, if you add a catalyst, right, then that's going to change our pathway. So our reaction does something more like this. So this would be the activation energy with a catalyst. Okay. All right, but so you're thinking, oh, it's going to speed up that reaction going in the forward direction. Now remember, when we have an equilibrium, that means the reaction is going both ways. So our reactants are forming products, but our products are also forming reactants. And so notice that when we added that catalyst, our catalyst is going to affect the reaction rate in the forward and reverse reactions equally. The reaction is going to speed up in the forward reaction, but the activation energy in the reverse reaction is going to be lowered by the exact same amount, because the reaction energy in the in the reverse reaction would be from here down to here. This would be the activation energy. Activation energy reversed. We'll use R for reversed. Okay, and so the activation energy with the catalyst would be somewhere like this, right? So this would be our activation energy reversed with catalyst. Okay. And so you can see that activation energy lowers the same amount in the forward or the reverse reactions. And so because of that, we have to keep track of that. Then the equilibrium doesn't get appreciably affected by addition of that catalyst. Now the Haber process is the exception, or one of the exceptions to that rule, just because the activation energy is so dang high. All right. So they threw this in here just so you can kind of visualize it here as well. Catalysts increase the rate of both the forward and reverse reactions, which is essentially what we just talked about. So essentially, when you add a catalyst, your equilibrium doesn't get shifted, it just gets there faster. Okay, and that's just because your reaction happens quicker. All right, so your activation energy is lowered and allows your equilibrium to be established at lower temperatures. All right, and so that's about it. What we're going to talk about equilibrium. There's quite a bit of stuff in this chapter, and so do your practice problems. Let me know if you have any questions, and soon we'll hit some more fun stuff. Don't forget, you can't lose the stuff. Acid-base chemistry utilizes equilibrium math a lot, so don't let it go away. Hang on to those ice table skills. All right, so let me know if you have any questions, and I'll see you on the flip side.